Hi students, go ahead and get out your chemistry notebook so you can take notes about polar bonds and dipoles. So how do we know if a bond is polar? Well, first we need to consider the electronegativity values of each atom that is involved in the bond. And as a reminder, electronegativity is the ability of an atom to attract electrons towards itself in a bond. That was one of the periodic trends that we learned about last fall. Do you remember how those trends went on the table? All right, well, let's look at this. So here is a chart of electronegativity values for the periodic table. All right, you'll notice the electronegativity values increase across a period, so that's from left to right, and they decrease down a group, so from top to bottom. All right, so if you look at the values here, you can see fluorine, that's in the upper right corner here. That has our highest electronegativity value. It's the most electronegative element. And francium, way down here at 0.7, is the least electronegative element. All right, so you should have a chart pretty similar to this, or at least one accessible in the Google Classroom. If your values are a little different from mine, maybe they're rounded, that's okay. All right, so you'll notice that there are no values written for the noble gases over here, like helium, neon, argon, krypton, and xenon. All right, well, why is that? Let's remind ourselves. So noble gases, they have those filled outer orbitals in their Bohr model, and that helps them be energetically stable. So they don't want to attract any electrons towards them or give any electrons away. This is also the reason why noble gases don't form bonds. And I put a little asterisk there because, like, usually there's always an exception to rules in chemistry. But noble gases, for what we're going to do not form bonds. Okay, so let's determine if a bond is polar. All right, we are going to calculate the delta En, or the change in electronegativity value between two elements. So that little triangle there, that's a Greek D or a Greek delta, which means change in or difference. All right, so electronegativity values are relative, meaning they don't have units, and it doesn't matter if the value itself is positive or negative. We only care about the magnitude of the value. So that means that it doesn't matter which value we subtract first. I always do it so I get a positive number. So I do my largest number minus my smaller number. All right, and then another reminder, bonding is actually on a continuum. There's not really like a cut and dry, like this is a polar bond, this is nonpolar, and this is ionic. So you can see here on this continuum that a nonpolar covalent bond, like hydrogen to itself of 0, then slowly the electronegativity difference will increase to polar covalent. So these are values between 0.5 and 2.1. And then values above 2.1 get us into the ionic range, where now no longer is the electrons in the bonds, they're not being shared at all. They're completely pulled over to the nonmetal from the metal. All right, so, but for our purposes, we'll go ahead and say that if your delta En is greater than or equal to 0.5, but less than 2.1, the bond is polar. And if your delta En is less than 0.5, the bond is nonpolar. All right, so we'll give ourselves some pretty strict parameters just for this practice. Okay, let's do an example. Let's calculate the polarity of a HCl bond. All right, so we're going to start by calculating delta En of HCl. All right, so on my table, I find each value. So hydrogen up here is 2.10, chlorine is 3.16. Now again, it doesn't matter which one you put first, so I always do larger minus smaller, so I get a positive number. So 3.16 minus 2.10 gives me 1.06. So this delta En is greater than or equal to 0.5, so our bond is polar. All right, so what does that mean when I look at the molecule itself? Well, this is our Lewis structure of HCl, so that means that chlorine is pulling more of that electron density of the bond towards itself. Chlorine feels more negative than hydrogen. it is more electronegative, and therefore hydrogen is more electropositive. All right, we can indicate this with something called a dipole. All right, so this dipole, it looks like I draw a plus sign and then the arrow. So the arrow is pointing towards the more electronegative element. All right, and so you'll notice the plus sign is on the more electropositive element. It's on the hydrogen. All right, so the arrow is always pointing towards the direction that the electronegativity is like being pulled. That's how I kind of imagine it. All right, example number 2. Calculate the delta En of a bromine-bromine bond. All right, well, the delta En of this is bromine minus itself, so we're automatically going to get 0. This is not greater than 0.5, so this bond is not polar. All right, so if I look at the Lewis structure, I don't need to draw a dipole because there is no difference in electronegativity. I can't point in any one direction. All right, example number 3, water. This is a really good example, and this explains a lot of the properties that we see with water. All right, so water has 2 bonds in it, right? There's 2 hydrogen-oxygen bonds, but let's just calculate 1 because it will be the same. All right, so delta En, so I find my value for hydrogen, which was 2.10. I find my value for oxygen, 3.44. I'm always going to do largest minus smallest. So 3.44 minus 2.10 gives me 1.34. That is indeed greater than 0.05, so this bond is polar. All right, so how do I draw this dipole on my molecule? Well, which direction do I need to draw the arrow? It's going to point towards the more electronegative element, so that is oxygen. All right, so I'm going to show that it's pointing towards the oxygen, and both of these bonds has a dipole that is pointing towards the oxygen. So if you think about it, the oxygen atom should have kind of a negative charge around it, where the hydrogen atoms are feeling a little bit more positive. All right, so we can represent both of them with our dipole arrow. Okay, go ahead and try these 3 practice problems on your own. Calculate the delta En for each of these, and then draw the dipole arrows if the bonds are polar on the Lewis structure. All right, so we have one for CO2, CS2, and SiF4. All right, we'll check these answers in class, but reach out to your teacher if you have questions.